Now here's a question that bounces in my mind a lot. How did something designed to make video games look cool become the powerhouse behind AI, blockchain, and scientific research? So what's so special about these GPUs, and why can't anyone compete with NVIDIA? What is it about these GPUs, parallel computing, and CUDA that makes them so dominant? And NVIDIA share price is skyrocketing. So I did some research trying to find an answer to this for myself, and as usual, I will share it with whomever wants to listen. So here we go. So let's start with the fundamentals, right? Most of us know that there is these CPUs inside of our computers, normal processors. Now, CPU stands for Central Processing Units, and they're great for general purpose tasks. They handle everything from running your operating system to managing complex applications. Now, GPUs, Graphics Processing Units, we know them in the form of graphic cards that are built specifically for graphics rendering. And if I'm not mistaken, designed originally specifically for video games. So the first questions that I had was why? What's the difference between the two, and what makes GPU better for graphics? So apparently CPUs excel at sequential processing. They're optimized to do one thing at a time very well. Like imagine a master chef meticulously preparing one dish after another, or a worker on the factory line. Now, GPUs, on the other hand, they're built for parallel processing, and that's the core idea that will make them what they are today. Instead of one master chef, imagine thousands of cooks, each preparing a small part of a dish at the same time. Graphics rendering, especially in real time, like in video games, is the perfect task for parallel processing because each pixel, vertex, or triangle can be calculated independently from others. Now, triangles. A friend programmer used to say to me, it's just triangles, man. That's all. Handling and computing triangles. So why triangles? Well, every 3D object you see on the screen is a mesh. And meshes are broken down into tiny triangles because of simplicity. A triangle is the smallest polygon that guarantees a flat surface in 3D space. So 3 points define the plane. There is this robustness. Triangles avoid the unwanted bending issues you can get with quadrilaterals or n-gons when vertices are not coplanar. They're hardware friendly. That means that the graphics pipeline like DirectX or OpenGL has been built around triangles for decades. So GPU drivers, shading languages, and rasterizers, they're deeply optimized for triangles. So it's not only about parallel computing. Modern GPUs actually have dedicated circuits, sometimes called triangle setup or rasterization stages, that are actually optimized to handle the math for breaking down triangles into pixels. Now, parallelism still matters. Even though there is specialized circuitry for triangle setup and rasterization, each pixel or fragment after the raster stage can be computed in parallel by the GPU's many cores. So you get these benefits of specialized hardware plus massive parallelism. So in short, triangles are not just an arbitrary shape. They are the foundation of real-time 3D graphics, and GPUs have both hardware and software pathways heavily optimized to handle them. Okay, but why are GPUs then used for AI and blockchain? Well, this is where things get interesting. GPUs are now everywhere, from AI training to cryptocurrency mining. But why? Training an AI model like GPT or DALL-E requires massive amounts of matrix multiplication. So these are mathematical operations that happen millions or billions of times during training. And GPUs excel at this because each matrix multiplication can be broken into smaller parallelizable tasks. GPUs can execute thousands of these calculations simultaneously. And blockchain systems like Bitcoin or Ethereum rely on something called proof of work, which involves solving extremely large number of cryptographic puzzles. And these puzzles are made up of simple repetitive calculations. Again, parallelizable, perfect for GPUs. So GPUs have become the workhorses of both AI training and blockchain mining because their architecture aligns beautifully with these tasks. Now, why does NVIDIA dominate the market? You might be asking the same questions I'm asking. Why NVIDIA? Why can't AMD or Intel just replicate their success? It almost feels weird that they have this monopoly. And the answer is twofold, hardware and software. So NVIDIA's GPU architecture is pretty special. They have spent decades refining these CUDA cores, tiny processing units inside the GPUs, specifically designed for parallel tasks. Now pay attention because this is what was confusing for me for a long time. CUDA. CUDA can refer to hardware and software. So first hardware and CUDA cores. CUDA cores are small specialized execution units inside the NVIDIA GPU. They're grouped into bigger blocks called streaming multiprocessors. As far as I understand, these units can have other cores as well, like tensor cores are more suitable for matrix calculations, or RT cores for ray tracing, for example. And these SMs will schedule and coordinate work across their internal cores. And each core can perform arithmetic operations like integer or floating point in parallel. So when you run code on the GPU, for example, matrix multiplications, these cores execute those calculations simultaneously. And CUDA cores are very flexible. They can handle multiple data types to support different workloads. And you can have anywhere from a few hundred CUDA cores in a lower-end GPU to several thousand in a high-end data center card. So the architecture scales up without drastically changing how you program it. But hardware is only half the story. So there is the CUDA software, which is the real secret sauce. And many of us have heard about CUDA, but let's clarify what it actually is. So CUDA stands for Compute Unified Device Architecture, and it's NVIDIA's proprietary software platform and API that allows developers to access and control GPU resources for general purpose computing. So in simple terms, CUDA makes GPUs programmable. It's not just about running graphics code anymore, it's about running any kind of parallel code on the GPU. And CUDA is like a translator between the developer's code and the GPU hardware. So why can't others compete? Because CUDA has been around since 2006, giving NVIDIA a massive head start. So over time, NVIDIA built a huge ecosystem around CUDA, including libraries, tools, and community support. And competing platforms like AMD's ROCm or Intel's One API are still playing catch-up. NVIDIA's success isn't just about having better GPUs, it's about having a better software ecosystem. So for the nerds among us, let's break down how CUDA actually works. When you write a CUDA program, you define kernels, which are small programs that run on the GPU. And those kernels are executed across thousands of GPU cores in parallel. You typically write them in C, C++, or Python via libraries like PyTorch. And the CUDA toolchain compiles them to run on the GPU hardware. So when you write this CUDA kernel, that code runs on many CUDA cores simultaneously. And data is broken into chunks and distributed across these cores. This means NVIDIA GPUs aren't just drawing triangles, they're performing millions of matrix multiplications, data transformations, and cryptographic calculations in parallel. And why does this matter for AI? Well, AI training frameworks like TensorFlow or PyTorch, they're heavily optimized for CUDA. So CUDA has different libraries like QDNN for deep learning. They accelerate these operations even further. And AI researchers rely on CUDA because it's mature, reliable, and incredibly well documented. But first, let's go back to architecture and architectural visualization and RTX. So I have been passionate about architectural visualizations for many years, and I learned how to render in 3D Studio Max 2 back in 1997, and even made a startup that used Unreal game engine for visualization in 2016. I'm still trying to get that one off the ground. But here I want to discuss shortly what does that RTX mean that NVIDIA introduced back in 2018, I think. When NVIDIA introduced the RTX series, starting with their Turing architecture, they brought dedicated ray tracing hardware to consumer and professional GPUs. And here's what that means. What is ray tracing? So photorealistic rendering is done using ray tracing. It is a rendering technique that simulates the way the light rays bounce around the scene to produce extremely realistic refractions, and shadows. And why is this hard? Well, traditional ray tracing is computationally expensive because you track each ray of light from the camera into the scene, bouncing off surfaces multiple times. And I mentioned 1997, and in those days we had to wait for like 24 hours or 48 hours for one single relatively photorealistic image to render properly. And that's how expensive these computations were and are. But NVIDIA introduced these ray tracing cores Again, first hardware to the rescue. Again, we see this hardware adjustment to solve a specific problem that is general enough to justify that. Now, talking about hardware specializations, there are even texture mapping units, specialized units that handle texture-related operations like sampling and filtering, which is key for real-time graphics. So we're looking at a very, very tight connection between hardware and software, which is their winning recipe. So we're now far, far away from the general purpose CPUs. So these RTXs are very important for architectural visualizations because they can create photorealistic renders in real time. Architects and designers can see near cinematic quality, lighting and shadows instantly. You don't have to wait hours for offline renderers anymore. We witnessed that especially in the Unreal Engine demonstrations. We saw how that's used in movies as well. And the client presentations are improved. Potential clients can walk through a virtual building with realistic lighting, reflections on glass and polished floors, dynamic shadows, making the design process much more immersive and convincing. So let's go back to NVIDIA. Will anyone catch up to NVIDIA? And of course, the answer is maybe. AMD and Intel are making strides with their platforms, and companies like Google and Apple are exploring custom silicon for specific tasks. But NVIDIA's combination of hardware and software dominance keeps them far ahead for now. So what's next in this GPU world? GPUs are no longer just for rendering graphics, so they're the backbone of modern computing. As AI models grow larger, GPUs will continue to dominate the space. Scientific simulations, financial modeling, climate research, they all rely on GPUs because of parallel computing. Real-time applications, AR, VR, and even self-driving cars rely on this GPU power. So what does this mean for us, especially in the building industry? For computational designers, engineers, and architects, GPUs are no longer just graphic cards. They're general-purpose supercomputers sitting in your desktop. And if you're working with AI, simulations, or generative design, learning CUDA can be important. NVIDIA's platform will likely remain central to innovation for years to come. So, next time you watch Jensen acting like a superstar, you know a little bit more about the reason behind that. And next time you see an NVIDIA GPU powering AI, blockchain, or computer simulations, remember, it's not just about hardware. It's about decades of innovation in parallel computing and CUDA hardware and CUDA software. So that's me trying to break this down, mostly for myself, and share it with you. If you enjoyed this video, don't forget to subscribe and drop your thoughts in the comments. And tell me, do you think anyone will challenge NVIDIA's dominance? And what excites you most about GPUs in the future? Stay free.